Hello guys, my name is Justin, and today we'll be talking about one of the more fundamental topics in not only labor economics, but also in life. So that topic is considered to be called a regression. So a regression, I guess the Merriam-Webster definition of it would be a statistical method of measuring the relationship between a dependent variable and one or more explanatory variables. So it's important because we want to essentially observe causal relationships. So causal relationships are very important. There's a fundamental distinction between causality, meaning one variable causes something else to happen, and correlation, meaning two variables move together, right? So I'll give you an example, right? Right now, I'm in upstate New York, right? It is very cold, incredibly cold, right? So with the cold, typically you would have increasing sales revenue for example, companies that sell jackets, right? Because it's very cold and that's something that could happen, right? Now with that, you'll also have potentially increased sales for things like hot chocolate to keep you warm, right? So those two variables move together, but you wouldn't say that people buying more hot chocolate leads to people buying more jackets, right? You wouldn't say that. However, I believe you would say, I am moving this board right now, right? This board is moving because I extended my hand and decided to move it myself, right? Also, this fell because I dropped it, right? So the latter would establish a causal relationship, right? The earlier no, right? So we want to essentially determine a model to help exemplify what I'm talking about here, right? So I'll give you an example, right? Okay, so we have y, which is our dependent variable, equals beta naught plus beta 1 x plus u, right? So we're going to break this down, right? So beta naught, right? These are sort of our fundamental parameters of the model. So beta naught and beta 1 are our fundamental parameters, right? Y and x are variables, right? They're considered random variables, and in certain cases they would be discrete random variables depending on the length of the outcomes that are possible given these two variables. But for now, let's just call this wage. The y represents the wage, the x represents schooling. This is a foundational sort of regression in labor economics, right? We're trying to measure the relationship between wages and schooling, right? Like I said, these two are fundamental parameters that describe the relationship between wages and schooling, right? Now, with that being said, u, right? U is considered the error term. These are factors that caused random variation within the model, right? Or unrecognized, unforeseen variation within the model, right? They encapsulate anything else that could potentially lead to bias or anything that takes us away from those causal relationships, right? So now, what this model is essentially saying is that there's a linear relationship between wages and schooling, right? So we can essentially, what I'm saying is we can observe changes in x, right? We can, for example, we can observe changes in x and deduce how changes in x specifically influence our dependent variable y, right? So if we have a bunch of values here, right? And then this is x, which is schooling. And then y, which is the wage, right? Essentially, what I'm saying right here is we want to establish a line that exemplifies the relationship between a 1 unit change in schooling and how that influences changes in wages, right? We want to find out where the line starts, and we want to find out what's called the rate of change of the line, which is represented by this beta 1. So essentially, beta naught, right, It helps determine the relationship between schooling and wages as a result of, it's basically giving you the y-intercept, right? So the beta knot is giving you how the line starts if schooling is 0. So if there's no schooling, what is wage, right? So we're calibrating sort of the beginning of that line, right? And the beta 1, if you allow me to do some math here, is essentially, if we take away, so this formula represents how systematic changes in X influence Y. That's our beta 1, right? So the name of the game, right, is to minimize the distance between, while also, we're obviously going to find what's called an OLS, or ordinary least squares estimate of beta 1, right? We also want to minimize the relationship between the data points, or in other words, I'm trying to minimize the sum of the squared residuals, right? So we want to minimize the space, try to minimize the space between the data points to establish a more clear-cut causal relationship between X and Y, right? Holding other factors constant, right? So in theory, let's just say, in theory, it could be 3,000 equals 1,000 plus, and then beta, so beta naught would be 1,000, and beta 1 could be 0.51, which basically means that if we're saying 3,000 equals 1,000 plus 0.51x plus u, right, we're saying that for each an additional year of schooling, that causes basically a 51% increase in wages. This is just an example of what I'm talking about, right? Or it can be a 51% decrease depending on the sign of this coefficient. But anyways, that's sort of the name of the game. We want to find a line that minimizes the squared residuals, or minimizes the space between the data points, right? While obviously establishing a beginning given beta naught, and take into account all the confounding factors, right? So that's the name of the game. Let's move on to the next part. So another property that we need to go over is we need to go over one of the fundamental assumptions for the model, right? So remember, the name of the game is to minimize the distance between the error terms and the regression line itself, or the sum of the squared residuals. In statistics terms, that would be what we would say, right? But now, that requires a very important assumption, right? An assumption in the sense that essentially we need to take the expected value of the random variable, which in this case is the error term u, and we need to set that equal to 0, right? Now, this may seem scary at first, but it's actually quite simple, right? So essentially what we're doing is we want to get a line that goes through this point, as I said, right? That minimizes the square residuals, right? In order to do that, we need to essentially normalize the distribution of the error terms, right? Now, what does that mean, right? It essentially means that we want to make this line centered about the distribution of the outcomes. So you want to get a line that's centered about the I know this is obviously this may be a bad drawing, but we want the average distance, right, between the average distance of the total unobservables, right, which could take on any of these certain outcomes. We want the average distance to be 0 as a simple assumption of the model, right? So, yeah, that's essentially what we're doing. We want the average distance to be centered at 0, so we can make a more accurate ceteris paribus assumption of changes in schooling, right, and how that influences wages, right? So that's one of the fundamental assumptions. The second assumption is that essentially has to do with conditional probability, right? So essentially we are assuming that the expected value of the unobservables, given that x, a random variable, is known, right? That essentially equals just the expected value of the unobservables, right? So in order to understand this fundamental assumption, we need to understand or reiterate the name of the game. So the name of the game is to develop a line, right, that essentially indicates that the unobservables, the error term, right, are orthogonal to x, meaning they're statistically independent from x, right? So how do we do that? We essentially say, for example, if U represents some of the things that could promote systematic bias, let's just consider U luck, right? Oftentimes, luck is a very intrusive variable that determine wages, right? Let's just say the expected value of luck given maybe 2 years of schooling is just equal to the expected value of luck, right? The expected value of luck, right, is independent of x, mean independent of x specifically, right? So that essentially, this fundamental assumption is important because it establishes the more ceteris paribus relationship that we want to see, the causal relationship that we would like to see, right? So by extension, if I said the expected value of U equals 0, then these three, all of this must equal 0, right? So just to review, we've normalized the distribution of the unobservables, and we're trying to make the line orthogonal, the unobservables orthogonal to x, which is years of schooling, right? So these are some of the assumptions that we have so far, and now we can start with the model. Okay, so the next part of the model is we want to essentially be able to leverage our assumptions. Remember, our assumptions are the expected value of the unobservables are equal to the expected value of the unobservables given that schooling is known is equal to 0. They're all equal to 0. Those are our fundamental assumptions. Now, logically, what we come next is we need to solve, since we care about the unobservables so much, we need to solve what equation represents the unobservables. So we need to go back to our fundamental equation of y equals b naught plus beta 1 x plus the unobservable, right? So now we want to solve for the unobservable, so we just move all of this to the right, right? So we end up with y I minus beta naught minus beta 1 x equals u, beta 1 and u, which are, what we would like to observe, right? So logically, if this is u and the expected value of u is equal to 0, right? Because of what we assumed before, then the expected value of all this would equal 0. Equals to 0. So essentially, what we want to do is we want to take an average of all of these values and set it equal to 0. Okay, so that's our first equation. This is our first equation, and in our second term, logically, is our second term. Okay, so we need to solve these two in order to come up with something more concrete, and that's what we'll be doing next. We'll be taking the expected or the mean of these two, right? So like I said, these are our terms, right? So logically, in statistics, it follows that if we want to evaluate, for example, let's evaluate these two. So if we evaluate these two in terms of this, right, if this is just an average, so for example, So if we add up n number of i's and then divide that by n, this just turns into a sample average. Same for xi. So essentially, what this is just spitting out is, okay, so essentially we're just spitting out this, right? So essentially we're just spitting out the sample averages, right? So now, if you want to solve for beta 1, we would just add, or I'm sorry, beta 9, we would just add that and beta 9 hat equals y bar minus, okay, so this is beta 9, and we could utilize this term and then stick it in to that second term in order to find essentially our second term and be able to extrapolate our slope formula, or slope indication of an OLS. Okay, so essentially we have, we solved for this, right? And now this is the second equation, right? But wait, I'm seeing something. Beta naught hat, right? We saw beta naught hat equals this. All right, so let's just plug this in. Okay, this is in parentheses, right? So we just sub that in, and now we want to do some math here. Y bar plus B1 X bar minus beta 1 0. Okay. Okay. So far we have this, right? We've just distributed the negative, so it's negative Y bar plus B1 hat X bar minus B1 XI, right? And the thing is, I could sort of distribute the XI, right? But that would be a big mess. Wait, that would be a big mess, right? So I have another idea. Wait, hold on, let me fix this camera. Okay, so sorry, I had to erase a lot of the board and move it to the top because I was running out of room. Anyways, essentially, what we have, this is what we have, right? So we want to make this so that we could solve for that beta 1 hat to get the slope indication, right? So now, I'm looking at this right now. This looks like a bit of a mess, but we could do some, manipulations. So the first part, it appears to me, we have the summation of xi y minus y bar, right? So that seems legit. So we could just do xi yi minus y bar, right? That seems fair. And then for the next part, we have a beta 1 hat that we would like to factor out because we want to solve for it. So we factor that out. And I'm also seeing 2 xi's and x bar, right? So if we factor the beta 1 hat to the outside and move that whole part to the right, because there's 0 over here, we could just essentially move that over there to make it just this equals this. We have beta 1 hat, and then we factor out the beta 1 hat and get the summation. Okay, and then xi times xi minus x bar. I'm pretty sure I did that correctly. So, okay, logically, it follows that this, via statistical formulas, is actually just equal to is actually just the sum of the product of the deviations from the mean, right? So that's the first part. Now, in regards to the second part, this in reality is just the deviations from the mean squared. So this is the sum, right, summation operator, of the product of the deviations from the mean, meaning this is one of our terms, this is the sample mean, this is one of the terms of the sample mean, right? And we also have, like I said, the sum of the deviation squared. However, to get this, we could simply divide out that, and this is what we got. So we divided this one out. So this is equal to beta 1/2. This part, essentially, sorry, I had to erase everything. But essentially, we just derived one of the most fundamental terms in regression analysis, which is the covariance of x and y over the variance of x. Now, what does this mean intuitively? Covariance of x and y over the variance of x. It means that it's essentially measuring the collinear movement of x's and y's, right, over the deviations of x from its mean. So he's basically saying the way we're analyzing the way these two variables move, right, with respect to their mean over how x moves itself, right? So for example, if this term, if xi, if these two terms are positive, right, then there's a positive covariance, then there's some sort of positive collinear dependence to the two variables, right? If one is positive and one is negative, then there's a negative covariance. We can't exactly delineate a positive correlation between the two, right? And how x moves itself, right? Or essentially, one of the other ways of saying this is the spread of the data points from the mean squared, right? From the sample mean squared. That would be actually a good estimation. So basically, this term right here eliminates a lot of the bias. It's saying ceteris paribus, holding everything else constant, this is how the two variables move with respect to x. So this is a good place to start. I want to talk more about the properties of this, and some other extensions in the next part. Lastly, I want to explain some of the indicators for how well our model interprets some of the variability. Okay, so for example, one of the fundamental variables, or one of the fundamental explanations, are called sum of the total squares. So the sum of the squares total, right, represents the total variability, right? So a good indication of that would be about right here. So the total deviations from the mean, right, will be represented by this area right here. Those are the sum of the squares total, right? So that's essentially, this length is composed of the sum of the squared, the sum of the deviations explained by the model, and the sum of the deviations explained by what we call those unobservables. If you remember in the beginning, I said we want to minimize the deviations from the observables, which is how we, from the unobservable, which is how we establish the line. Now, the sum of the squares, the sum of the sort of explained by the model, we have to take the deviations from our predicted values from the line, which are y hat I and the mean. A good representation of that would be about this length over here, right? And the sum of the square of residuals with respect to the unobservables would be about right here. So this area plus this area equals the sum of the squares total, right? And lastly, another measure that's frequently used in econometrics and with certain areas is R squared. So R squared is basically the ratio of the sum of the deviations explained by the model to the the total deviations, right? And this is denoted as R squared, which basically represents the reliability of the model in terms of interpreting the deviations explained by the model and the total deviations. So it's a good indication of the reliability of the model. It's a useful measure in that regard. It doesn't really do much to establish causality, however, but that's, sort of the job of R squared. So anyways, that's all I want to talk about for today. We established the slope indicator of OLS. We've established some of the indicators of the goodness of the model. And this is fundamental to a lot of different, policymakers and consulting firms and whatnot. So I hope you have a good day.